I will start recording now. Good morning, everybody. Welcome again for this colloquium at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Daniel Scherer from the University de Genève in Switzerland. And he will talk about empirical and physical properties of Lyman continuum emitters. Daniel will be properly introduced by Dr. Isabel Marquez, our PI of the Severo Ochoa program. Isabel, please.
Thank you, René. Hello, good morning. Thank you, everybody, for being here again at this Severo Ochoa web colloquium. This time it's an online format. And thank you very much, first of all, Daniel, for having accepted our invitation that I'd like to officially extend to an in-person one for next October. So thanks so much. Daniel Scherer is an associate professor at the Astronomy Department of the University of Geneva since 2008, on leave of absence from the CNRS, Centre National de la Recherche Scientifique Française. He received his PhD in astrophysics from the University of Geneva in 1995. And he then got LzLCS from the Swiss National Science Foundation, postdoctoral fellowships, first at the Space Telescope Science Institute in Baltimore, in the United States, and then at the Observatoire Midi-Pyrénées in Toulouse, in France. In 1999, he obtained a research position at the CNRS in Toulouse. His current research interests cover the formation and evolution of galaxies, star formation in distant galaxies, the first galaxies, and the early universe. He is an expert in stellar evolution, in stellar population modeling, radiation transfer, and multi-wavelength observation and modeling. He is the principal investigator of the survey Deep Spectroscopic Insights on Star Formation Galaxy, 2.2 gigayears after the Big Bang, that has been accepted for the James Webb Space Telescope. He has co-authored over 400 journal and conference papers in astrophysics with more than 25,000 citations. He has been SOC member of numerous international conferences, including IAU and the European Astronomical Society Symposia, and chair and co-chair of the organizing committee of 2 international doctoral schools and several international conferences and workshops. Among his reviewing activities, he has been member of the Hubble Space Telescope Time Allocation Committee and the ESO Observing Programs Committee. And since 2018, he's member of the Mosaic Steering Committee, Mosaic, the instrument for its second light of the ELT at ESO. In addition, he has been president of the Swiss Society for Astronomy and Astrophysics until 2021, secretary of the Interdivision Commission Galaxy Spectral Energy Distributions of the IAU. Daniel Scherer is involved in teaching duties at the University of Geneva, where he's the coordinator of teaching activities and the director of the Master in Astrophysics of its astronomy department. He has supervised a 10th PhD thesis, a similar number of postdocs, and numerous master students. As René already said at the beginning, he's talking today about empirical and physical properties of Lyman continuum emitters. Thank you again. Thank you very much, Daniel Scherer. The floor is yours now.
Well, thank you very much for the invitation again, Isabel and Pepe, and thank you for the introduction. Do you see my first slide?
Yes.
Yes.
Okay, good. So what I want to tell you about today is where we are, what we know about what we call Lyman continuum emitters, or sources of cosmic ionization, or analogs of these sources. So basically, I will take you through a short introduction to explain a little bit the global context and what we are after. And then I will mostly talk about results we've obtained since 2016 using the HST and recently a HST Large Programme, the Low-z Lyman Continuum Survey. And that will allow us to talk about the physical properties of Lyman continuum emitters and how we can recognize these galaxies. And then I will wrap up the whole seminar. So what we are talking about is what we're interested in general is the early universe, and specifically the period which we call cosmic ionization, which is early period, basically during the first giga years after the Big Bang, where the first stars formed and where they have transformed the universe. That is best expressed or shown as with numerical simulations, as we can see here. For example, you have a simulation which shows the evolution of dark matter and baryons and the ionization structure of the intergalactic medium. And as you can see, with time, the first stars inside the first galaxies, they create ionized bubbles which extend out of the galaxies, and they progressively with time they transform the intergalactic medium from neutral, how it was after recombination, after the Big Bang, to ionized, fully ionized over roughly 1 giga year. So this is let's say the numerical simulations which guide us in our. That's the picture we have right now, but it is a theoretical picture which is backed by some observations, but obviously we do not know much about this period on the empirical side. We have, for example, constraints from the CMB background and from Planck measurement, which tells us roughly the total amount of free electrons along the line of sight, which gives a constraint on basically when the cosmic ionization ended. And this can also be measured by different ways by different tracers of neutral hydrogen, for example, in Lyman alpha emitters, in the Lyman alpha forest, and so on, which allows one to trace roughly the history of the evolution of the neutral gas fraction with redshift or with cosmic time here. So we have these rough indicators or telling us on how this process went approximately and over which times, but we don't know for now what are the main sources of this cosmic ionization. And we think in general that this could be stars or this could be quasars. And there are in the literature many other alternatives are being discussed. There have been exotic suggestions that dark matter decay, for example, or mini quasars or X-ray binaries could contribute to significant or different amounts to cosmic reionization. This is presently basically unclear and debated, and the source of study, of course, empirically also. Overall, we think that galaxies are probably the main source of the reionization of hydrogen, and quasars are mostly responsible for the ionization of helium plus, which happens later on. That is what we think, but we want to measure this, of course, empirically, and for that we need to go out and make observations and understand and observe all these things and measure and so on. In a nutshell, why do we think that galaxies could be the main drivers of cosmic ionization? That comes from the following observations we have so far, which are illustrated here. This is the luminosity function of distant galaxies. So how many galaxies there are as a function of UV magnitude. And what we find consistently is that when you go to fainter and fainter objects, the number of such galaxies increases quite rapidly. And if you assume, for example, that the average galaxy which we count here, that approximately 10 to maybe 20% of the ionizing photons which are produced by these star-forming galaxies manages to escape the galaxies into the intergalactic medium, then you can come up and count, and you can see that basically this would be enough to reionize the universe by redshift 6 as it is observed, if galaxies produce and the photons escape. So that means indeed that there is this if, and we need to be able to see this. So we need to be able to show that, that on average, really an escape fraction of the order of 10 or 20% manages to get out of galaxies, and that their production rate is sufficient to do that, and that there are sufficient of these galaxies. So in a nutshell, that's the task. And because finding distant galaxies and Lyman continuum, excuse me, I just closed the window to reduce the noise. Yes, so we need to find galaxies which show escaping ionizing photons. And these are what we call Lyman continuum leaking photons or Lyman continuum emitting photons. And of course, people have studied, have tried to find such galaxies for quite a while at different redshifts. But basically, I'm not going to summarize the whole history. In general, it is thought that most galaxies in the present-day universe are relatively nearby and do not show any leakage, significant leakage of ionizing photons, because galaxies contain a lot of hydrogen, and when the ionizing photons are produced, they are just absorbed locally in the galaxies. They create nice H2 regions, but that's it. We think that most of the ionizing photons produced inside galaxies, they stay inside the galaxies. They don't manage to get out. But as I just told you, if we want to explain cosmic ionization, it means that the average galaxy needs to lose a significant fraction of the ionizing photons. So maybe things have changed when we go to the early universe, and things are more transparent galaxies, or produce more, and so on. So that's what one needs to do. And as I said, there have been many searches, and it's the difficulty is how to identify the sources of reionization, and then to measure basically their physical properties. And in a nutshell, what we need to measure to explain cosmic reionization is we need to produce, first of all, how many galaxies there are produced. So that is the UV luminosity density, or the star formation rate density. Then how many ionizing photons these galaxies produce, for example, per UV luminosity. And then we need to measure the average escape fraction. And that gives us the total ionizing budget, the total photon production rate of this population. So this is what people have tried to do. For a long time, people have tried to measure the escape fraction first. And until 2016, I think one can summarize the situation was basically like that. A lot of upper limits, a few detections here in relatively bright galaxies, but we had not much success until then. And I want to show you now in this talk, basically, is that since 2016, in fact, things have progressed a lot, both at high redshift, so this is in the order redshift 2 to 3, and at low redshift with HST. And for example, the progress can be summarized in this picture here, which was produced by Alberto Saldaña Lopez, who is a PhD student right now with me in Geneva, and who is actually following a school in Granada this week or last week. So in this figure shows, these are points where we have individual measurements, detections and non-detections of escaping ionizing photons. And we have here on this figure roughly 100 points. So we have now made significant progress, and we have found many galaxies. I mean, these are not huge numbers, but at least we have made significant progress, and we can study the properties of these galaxies as I will show in the rest of my talk. So how do these galaxies look? Lyman continuum emitters, for example, here is a case, one of the best known and best studied high redshift galaxy at redshift 3, which was discovered by Eros Vancella. These figures are very complicated, but it's just to show you that, this galaxy is nicely studied in HST at different resolutions. We have spectra of it and so on. And basically what you can see is that there is, for example, an image here, which is taken in an HST filter, which looks at wavelengths below the Lyman limit. So at below 900 angstroms, and you see this galaxy clearly emits flux there. There is no other galaxy around. You can also see the Lyman continuum flux in the continuum, and you can study the properties of this galaxy. And you define basically that we are talking about a relatively low mass galaxy with low metallicity and with very strong lines, high excitation. There are other galaxies, Lyman continuum emitters, at high redshift. This is probably the most spectacular case. It's a strongly lensed system at redshift 2 approximately, which has been discovered by Rivera Thorsen and collaborators. And now we have, in fact, many images. So we have this galaxy is strongly stretched. It shows clusters which are multiply imaged. Every of this number here is a single image, is an image of a very compact star forming region in this galaxy, but it's just a multiple image of the same cluster. And here you have an image in the Lyman continuum. So you can see again, this object is very well detected and studied and can be studied in detail, as you can find in the literature. At redshift 3, there have been many other surveys also with Keck, especially by Steidel's group and also with the VLT. which have been able, both with imaging and spectroscopy, to find Lyman continuum emitters. And here you can see such examples. Here you have the rest UV spectrum. Here you have Lyman alpha, and then you see here is the Lyman limit. And you see that in some galaxies, there is an excess of flux here. And this is the emission in the Lyman continuum. So these are photons which escape from these galaxies, and they manage to come to us, down to Earth, even if there is some absorption of the intergalactic medium on the way from redshift 3 to us. So we have several examples studied here. And then we have also made significant progress at redshift 0.3, which will be most of the topic I will talk about today. And namely, these discoveries have started with HST when we pointed with Yuri Izotov and colleagues in Geneva and in other locations. We have studied a class of very compact star-forming galaxies at redshift 0.3. And this was the first detection here of the Lyman continuum, of a strong Lyman continuum in such a galaxy. I will come back to this in more detail. Just to finish my introduction, I want to say that, at low redshifts since 2016, now we have been able to gather a large set of multi-wavelength observations, which means that we have different numbers of galaxies observed basically from the Lyman continuum to the normal UV. We have detailed absorption lines, we have overall spectra, we have SDSS spectra, we have X-shooter spectra, we have, and so on. So we have quite some range of tools and information which allows us to study in detail these galaxies and to learn a lot about their physical properties and the physics of Lyman continuum escape. And it's summarized in some of these papers here, and I will talk about it basically now. So as I said, one of the questions is how do we find actually galaxies whose Lyman continuum radiation can escape? And the question is how to find them, but you may also ask why is it so difficult to find them? And why do we, why is that important? What you have to recognize is that, we can at redshift 3 and at redshift 0.3, we can point our telescopes or spectrographs to the Lyman continuum region and try to see if there is flux and then study these galaxies. But in fact, when we want to explain cosmic reionization, so the epoch above redshift 6, that's where we would like to play the game and count how many galaxies are there, whose ionizing photon escape, etc. But the problem is that this will never be possible because precisely the galaxies in the epoch of reionization are in an area when the intergalactic medium is not transparent yet. So we will never be able to see basically through the intergalactic medium at a very high significant redshifts Lyman continuum radiation. So that means that we need to develop, also for practical reasons, we need to develop techniques to find indirectly these Lyman continuum emitters. And that is a significant part of the job we've been doing and we are continuing to do. In 2016, when we started this new observational program I will talk about, the different people had suggested basically these following methods here to find Lyman continuum emitters. So this was basically a suggestion that there could be high O3 to O2 ratios, so strong emission lines with a high ratio. We should look at galaxies with peculiar Lyman alpha line profiles, or at galaxies with particularly weak UV absorption lines. These were the suggestions. And now, of course, we may ask, why would that be? What would be the relation, the connection with Lyman continuum escape? And it's quite easy to understand the basic principles which motivate that. So, for example, imagine that you have this is a simple sketch of the interstellar medium in a galaxy. You have stars here, the observers on the right, and you have clouds of interstellar medium. But if between these clouds there are free regions where Lyman continuum radiation and other radiation can propagate, that's the way you can get Lyman continuum escape. And then that would mean that, the regions where there is gas, this is where you have absorption lines which are produced. So, you could have a mixture of strong absorption lines which are formed in these clouds and some gas which escapes freely. And that would translate into UV absorption lines, which we usually see or often see saturated here that these intrinsically saturated lines would not be saturated because you have some radiation which escapes directly. So that was a suggestion that we could recognize leakers through these, covering factors, absorption lines which are not deep, which would correspond to a patchy interstellar medium. The other suggestion was motivated from radiation transfer models from my colleague Anwar Hamir, who basically looked at the radiation transfer of Lyman alpha in such galaxies where you have channels which are free, or in fully ionized galaxies. And then she predicted that the Lyman alpha line profiles which you would expect would be basically centered at 0 because Lyman alpha photons can escape in this case here, or if there is some scattering, but a small amount of scattering because you have a little hydrogen on the line of sight, you would expect double peak profiles with very narrow separations. So this was the second method which was suggested. And the third one, which was floating around in the literature, is a very basic method which suggests that, if an entire galaxy could be described by a single H2 region, this is the typical ionization structure we expect. O3 in the center, O2, and then neutral oxygen at close to the Strömgen radius. And that's the way normal H2 regions look, right? But if you had a galaxy which was completely ionized and some photons missing, some photons escaping, it would basically, it would basically correspond to this kind of situation where you simply cut your H2 region somewhere, and therefore low ionization lines of O2, for example, some of it would be missing. And in this case, of course, the ratio of O3 to O2 would go up, and maybe that's a way you could recognize such Lyman continuum emitters. So, motivated by these basic questions, by these basic methods, we actually went out and put together a HST proposal in 2014 or 15. And the goal was precisely to select galaxies for high O3 to O2. We wanted to look at compact galaxies because we want to have strongly star-forming galaxies, which we can capture entirely in the aperture of COS with the HST. And then we chose a redshift 0.3, which is not a magical number. It's just adapted to the sensitivity. It's where the Lyman continuum comes to region where the instrument on HST COS becomes sensitive. So we did initial program. We proposed to observe five galaxies. We wanted to get Lyman continuum, Lyman alpha, and UV absorption lines to test these methods. These are the galaxies we looked at originally. Compact in Sloan, of course, we want to select only star-forming galaxies. And that's the way we got our first observation. The first galaxy HST looked at, no, it was not this spectrum here, but it showed a Lyman continuum escape. So we were very happy, of course, but also surprised. And then when our observations went on, we ended up having actually 100% detection rate. We continued this program later on. And in 2 cycles, we got another, in total, we got basically 11 galaxies. And in all of this program, it was really amazing. We had 100% success rate. So which tells us, that somehow our selection criteria were very efficient. And then what did we learn from that? Yeah, we saw that, for example, there was some kind of vague correlation of F escape with O3 to O2, but when we got the larger sample, things became a bit more complicated. A very interesting result we obtained is regarding the Lyman alpha. So indeed, the Lyman alpha line profiles of these galaxies looked pretty much the way my colleague Anwar had predicted. They show double peaks, in some cases triple peaks with narrow peak separations. And indeed, what we find is that the escape fraction of ionizing photons correlates very strongly with the separation of the peaks, which is basically what was predicted by these radiation transfer models. Where are we actually with time? Just 20 minutes on, right?
Yes.
Okay. Good. So the next observations we obtained, as I said, the next thing we were interested in, it was looking at the UV absorption lines, because as I mentioned, this was the third method which was suggested. So what we did indeed is look at this sample of leakers which we had at this time. We also looked at other galaxies in comparison, and we tried to study the UV absorption lines. And this was work which was done with a master student at that time, Simon Gazagne and John Chisholm. In a nutshell, as I said, what we wanted to do is basically see, whether the interstellar medium in these galaxies, what is the geometry, if it behaves like this picket fence model, as we say, which may include some dust and so on. And to do that, what we have to do is, basically model with this simple geometry, so the radiation transfer in this simple geometry, look at the different absorption lines which we can study, and then we have to fit simultaneously the stellar continuum, the UV attenuation, and the interstellar absorption lines. So that's what we do, and here is the data we are using for that. So this is a zoom on some of the spectra which we have obtained. Basically, they are all in the very blue part of the UV, and you can see, we detect stellar lines here, and then we detect absorption lines of the Lyman series, but also metal lines. And the first thing, we can notice qualitatively is in fact that there is a big variety in these strong absorption lines of the Lyman series, for example. We expect from simple estimates, we expect that these lines would be saturated, but what you can see is that in fact in the galaxy, which is a confirmed Lyman continuum leakers, this flux here at the bottom of the line is not zero. In contrast, there are objects where the lines are really black, which is what you expect if you have a strong saturated line and a lot of hydrogen in the galaxy. So we see already empirically difference between that. And when you do things more quantitatively, you can in fact see, you can show that we have indeed high column densities in these galaxies. We can measure it, for example, from unsaturated O1 and using the metallicity, but that the galaxy, this gas is not covering uniformly the galaxy, because the H1 lines here, there is flux which is escaping, and if in these galaxies. So indeed, with these measurements of the column density and the observations of the H1 line profile, you can show that the geometry of the interstellar medium is indeed porous, and that we must have escape of UV and including Lyman continuum photons through holes. And that is another interesting thing which we learn, which is not really surprising, but it's interesting to understand how the escape happens. And then we can see also that there are correlations with covering factors and so on. So we basically rule out this kind of geometry here for most of our Lyman continuum emitting galaxies, and think that galaxies are more appropriately described by this kind of geometry, which is of course also a simplification. Now, another interesting exercise we did with these galaxies and later on is actually to see, if we had only UV absorption lines, could we predict the escape of ionizing photons? And yes, in principle, if you have a simple geometry, you can predict that. And you can just write down the equation of a radiation transfer. And if you are able to determine simultaneously the UV attenuation and the covering factor, so the geometrical, how many lines of sight are free, basically, then you can determine the escape fraction. And this is what we did for these galaxies, where we have the true measure of the escape fraction, but we have also the UV absorption lines. And you see in this first paper, we found a reasonable correlation between the two, which has now been improved in this recent work from my student Alberto Saldaña Lopez, including nearly 90 galaxies. So we find indeed a scatter between the true observed escape fraction of Lyman continuum photons and the one we predict just from the UV absorption lines. But overall, the correlation there is a correlation, and we can predict to some extent the Lyman continuum escape, even if we cannot measure it. We have also tested this for other galaxies, at different redshifts. For example, in this case here of redshift 2 galaxies, where we have UV absorption lines, and HST has measured an upper limit for the Lyman continuum, and our predictions are compatible with the observations. So in a nutshell, we have in few recent years, we have validated basically these 3 indirect probes of Lyman continuum escape. which either, to different degrees, we can use them to predict quantitative escape fraction. We have seen that there is some scatter, but I will show more about that. But overall, these observable properties show a good correlation with the escape of ionizing photons and can therefore be used, for when you observe at higher redshifts. Now, what else have we learned about these galaxies? What are the physical properties of these galaxies? So first, looking at the sample of compact galaxies, the green P-like galaxies, which we studied initially. So as I said, they are by selection, they are compact galaxies. Their sizes are, in the UV, they are less than 0.4 kiloparsecs. And in fact, that is something which we think is the kind of typical sizes at high redshifts. Here you have a size measurement as a function of redshift, also in the rest frame UV. And you see these UV sizes, they are comparable to the sizes we have in our compact low redshift galaxies. What other properties we can measure from them? We can basically measure everything. I mean, we have integrated spectra only, but we can determine, star formation rates. We can estimate the masses. We can estimate ages. We can also determine stellar masses, metallicities, and so on. And these are the overall properties of our compact star-forming Lyman continuum emitters. So they turn out to be dominated by young stellar populations. They have relatively low masses, relatively low metallicity, but not extremely low metallicity, and low amounts of dust. Let's keep those in mind for later on. We have also been able to constrain, but I think I will skip over that. We have also been able to empirically constrain the UV attenuation law in some of these galaxies, which seems to be steeper than what we typically assume in star-forming galaxies, and more similar to the SMC. Besides measuring the escape of ionizing photons, what we're also interested in is measuring how many ionizing photons these galaxies produce, because that the product of the production times escape tells us how many ionizing photons actually really end up in the intergalactic medium. And in the initial sample, we already saw that in these compact galaxies, at least, the ionizing photon production was slightly higher than the standard value, which is what was assumed, in these simple estimates to see if galaxies can reionize the universe. So we end up with galaxies which are indeed, as we can see here, which have properties, which are quite comparable to this redshift 3 galaxy I mentioned earlier. So you see low metallicity, similar mass, 10 to the 9, strong Lyman alpha emission, and this redshift 3 galaxy has also high O3 to O2, strong lines. So in fact, the early leakers we found, these compact or green P-like galaxies, they have at redshift 3, they have properties which are comparable to at least one of the high redshift leakers. If we look a little bit more carefully, indeed, we find that all our leakers, they have strong emission lines, which in fact, in strength, they become comparable to high redshift galaxies. Sorry, this is better summarized in this figure here, which shows you a determination of, here you have the sum of H beta and O3 equivalent widths as a function of redshift for galaxies in a certain mass range. And what you see, what people agree on is that overall, when we go to higher and higher redshifts, the emission line galaxies become more strong, or the typical strength of the emission lines increases when we go to higher redshifts. So our galaxies, they are sitting at redshifts 0.3, of course, and they are very rare galaxies, in the SDSS. They are very rare in the nearby universe. But the equivalent widths of the galaxies we have chosen are by selection, they are very strong. And in fact, they are up here. They are roughly 1,000 in H beta plus O3. So you see our rare objects, which we just picked because we think they are interesting to study, and we can study them easily at redshift 0.3. They seem to have properties which are in fact, very comparable to those of the typical galaxy in the epoch of reionization. And we can play this game more precisely. Of course, we can compare every quantity we can determine, equivalent widths, not only stellar masses, sizes, star formation rate, compactness, and so on, we can compare them to the properties we know so far from the high redshift galaxies. And in fact, they are in every quantity we can measure, they are comparable to the typical galaxy at high redshifts. And from this, we conclude that the objects we are studying are good analogs of the average galaxy in the epoch of reionization. And that is, of course, an important thing, because it tells us, that what the galaxies we are studying, we think that's their properties, and is telling us something about the way high redshift galaxies behave. And when we sum all this together, we have also, this is another figure which shows the ionizing photon production of different types of galaxies. And overall, what people have found is in a similar way as the average equivalent width of galaxies increases when with cosmic time, we also find that the average ionizing photon production rate of galaxies, of star-forming galaxies, increases when we go to higher redshifts. And there is also a correlation of the photon production with the strength of the emission lines and so on. And our galaxies, they are basically always located at the high end. So that is the picture we have basically obtained from this initial sample of roughly 15-20 galaxies at low redshifts. And now I want to spend a few more minutes on the LzLCS, how we call it, which is a HST Large Programme, which has recently been completed, and from which we've published the first few papers this year. So what is this program? It's a program whose goal was to provide, a large, or maybe the first statistical sample of galaxies where we have measurements in the Lyman continuum. And the idea was to probe a wider parameter space than before. So whereas before we focused on very compact galaxies with a high O3 TO2, we wanted to broaden our range of parameters, to see how, in the end, does this escape fraction, does it really depend strongly on O3 TO2? Or what is it if we go to less compact galaxies, and what if we go to less blue objects, etc. So that was the overall goal of this program. So we observed 66 star-forming galaxies at this redshift with HST, and the program was completed, and we had a few first few papers published. Survey paper published from Sophia Flury, and other papers from my student, and so on. So what we obtain overall, when we combine our previous measurements from HST with the new 66 observations, we have a sample of 89 galaxies, and from those we have roughly 40 to 50 galaxies which are significantly detected in the Lyman continuum, so at levels larger than 2 to 3 sigma. We find, actually, here you have a figure showing the escape fraction and the upper limits here. So we find a wide range of escape fractions, and we find also quite a number of, so I need to get rid, a large number of galaxies which are relatively high escape objects showing high escape fractions. More in depth, so what do we find from these properties? I will show a few figures, a few slides where we show in the same fashion, basically the correlation between Lyman continuum escape fractions, which we determine in this survey by 2 different methods. I'm not going to explain for now, I think. And here, for example, you see the escape fraction of the ionizing photons as measured from H beta, and from the UV absorption, from the UV modeling as a function, how it correlates with Lyman alpha. And on the right, we show the fraction of galaxies which are detected in the Lyman continuum as a function of the same quantity. So what you can see, for example, on this slide is that, on average, the escape fraction of ionizing photons increases with increasing Lyman alpha strengths, and that the fraction of galaxies which are Lyman continuum emitters also increases when you go to higher and higher Lyman alpha emitters. We confirm also the correlation with the Lyman alpha line profile, which I already showed. And then we find other correlations For example, here is the result as function of O3/202, which I showed before. So we still have a large scatter, but some correlation here. And definitely, if you select galaxies which have a high O3/202 ratio, you are more likely to find Lyman continuum emitters, which explains basically, why initially we had this 100% success rate. What other correlations do we have? We have strong correlations between the escape fraction and the compactness of the galaxy in the sense of the star formation rate surface density. You can see the behaviors here, and also the detection fraction increases with compactness or with star formation rate surface density. And what does that tell us probably is that, when you have more and more compact galaxies, or in other words, if you have a high star formation intensity deposited in a small volume or on a small surface, that probably facilitates the escape of photons through channels or holes in the interstellar medium because of some mechanical feedbacks. That is at least the physical reason which we think could explain such a correlation. We also find, and now with much larger samples, correlations between the escape fractions and the strength of the absorption lines. Here is the residual flux in these absorption lines, or the equivalent width of the absorption lines. This is what I've shown in more detail for the small sample, but it's nicely and much more constrained right now. And again, this behavior of the absorption lines can only be explained if the interstellar medium is patchy, so contains channels or holes. And in fact, an important result, which Alberto Saldaña Lopez has shown also, is that he can also pin down where actually the dust is sitting in the galaxy, because we see also that there are correlations between escape fraction and dust. So not all the Lyman continuum emitting galaxies are dust-free. You can see the more dusty the galaxy, the smaller is on average the escape fraction. And in fact, Alberto has also been able to show that actually the dust is located in the same location basically as the metals. So it's not a foreground screen, but the dust is also located in these patches of gas in the galaxy. So this is what we have. These are the correlations we found. We also find, of course, some quantities which do not correlate with F-escape. For example, it seems that there is no strong or clear correlation of the escape fraction with UV magnitude, which maybe tells us, that the absolute scale or mass of the galaxy does not really matter to first order, but it's more maybe, the compactness and so on. But these are things which are still a bit debated, and there may be conflicting results on this trend with UV magnitude. So in a nutshell, I think to summarize, I have 3 slides showing what are the main lessons we learned from these Lyman continuum emitting galaxies and from the non-detections also. So what we learned first is that, there exist strong Lyman continuum emitters at low redshifts. They are just very rare. In fact, we can find a range of intensities of Lyman continuum escape, strong and weak ones. We can find some relatively UV bright galaxies which have a lot of ionizing photons, which means that not only the faintest low mass galaxies can contribute to cosmic reionization, but we don't know exactly how much is the relative contribution between the faint or the bright galaxies. This we need to work on still. What we also conclude is that the majority of the strong Lyman continuum emitters, they are compact, they have high surface densities, they have strong emission lines, they have somewhat low metallicity and low mass, and they are relatively dust poor. And again, as I mentioned just before, these galaxies, these strong Lyman continuum emitters, and their observed properties are basically very similar to the properties of the average high Z galaxy, and therefore they should be good analogs of those galaxies. As I also mentioned, the other thing we learned is about the geometry and the escape mechanisms of the ionizing photons. We know that we cannot describe the galaxies just as simple spherical objects which are completely ionized, but in fact the galaxies must be described by this kind of structure here, as I said before, with holes where the UV ionizing photons which means also that, if we want to seriously and quantitatively model these galaxies, we need to account for this complex geometry, so that in fact we need to have we need to abandon this 1D models, and in fact we need to do what we call, for example, multi-sector models, which are at least a superposition of two phases. You need to describe at least the relatively low density channels and the other clouds, but maybe we need more components for that. And I have no time to dwell on that, but we have shown in the paper with Lise Raman-Bazon in 2020 how in fact such a multi-sector models with just two components can actually very well reproduce the emission lines and the absorption lines of the Lyman continuum emitting galaxies. But if you just try to describe these galaxies with a single H2 region or a simple model, this is not possible. You are able to reproduce some observables, but not to get the consistent picture, and you will not be able to infer the escape fraction. Yes, I think I have a few more minutes left. I think I come to the end. So the third main lesson we learned from all this exercise, or from looking at all of these galaxies and discovering finally significant samples of Lyman continuum emitters, is that indeed we have been able to find different indicators, indirect indicators of Lyman continuum escape, which, as I said, are fundamental if we want to measure and to say if a galaxy at high redshifts, is emitting Lyman continuum photons or not. So we have right now this list. I mentioned already at the beginning the Lyman alpha emission and the absorption lines. But in the meantime, people have been busy and have worked and have been creative. And we have found also other indicators. For example, recently we discovered that the strong Lyman continuum emitters also show intense carbon-4 emission, which you can read in this recent letter here, which indicates that possibly carbon-4 and carbon-3 can also be used as indicators of Lyman continuum escape if you have access only to the UV range. And that's, for example, something which we are going to observe with extremely large telescopes from the ground and very sensitive spectrographs, as MOSAIC, which was mentioned, we are working on, and the Spanish community is also participating, of course, in this powerful instrument for the ELT. This will be able to measure all this UV part for the high redshift galaxies. And then people have come up with other measurements and methods to determine with different degrees of confidence, let's say, whether galaxies are Lyman continuum emitters or not, or even with some accuracy to being able to predict the amount of ionizing photons which are escaping. I will have no time to discuss that, but it includes, for example, the use of the magnesium-2 doublet, sulfur-2 lines, etc. So this is where we are right now, I think. And what we are going to do in very soon with the James Webb is, going to apply all we have learned from these low redshift samples to the early universe. And that means, of course, different topics. In particular, one project I'm leading, which was mentioned, will be observing known Lyman continuum emitters and the control samples, so objects where we also know that they are not emitting Lyman continuum around redshift 3. Basically all the known galaxies which have been found so far by Steidl's group and other groups from Richard Ellis with different methods, they will be pointed at by the James Webb with the NearSpec spectrograph, which will take rest frame optical spectroscopy of these galaxies. So it will cover this whole spectral range here, where we have all these diagnostics of sulfur-2, which are discussed, O3 magnesium-2, and so on. And for those galaxies, we have already, of course, the UV observed, with Keck and VLT and so on. So what we will have once this program is completed is we will have a complete set of observations of basically all the known Lyman continuum emitters and control sample from the UV to the rest frame optical. So, and we will have access to all of those diagnostics. And we can check how these diagnostics behave at redshift 3. Do they also work? Do they work in the same way? And of course, in addition, we can use all those optical emission lines to determine to study the physical properties of the interstellar medium in these galaxies, densities, metallicities, and so on. So we have an extremely rich database And this is the kind of data we expect. This is a simulated spectrum of a Lyman continuum leaker observed with James Webb. So you see, you can study in exquisite details these emission lines and do physics like we are doing right now at redshift 0.3. And with that, of course, we will have, basically probes we will have 2 reference samples of Lyman continuum emitters and a control sample, one at redshift 0.3, which is 10 gigayears basically after the Big Bang, and another one at redshift 3, which is 2.2 gigayears after the Big Bang. And what this will tell us is from this we will be able to say, do things change? Do the interstellar medium properties in these galaxies change? Do the diagnostics change or not? And of course, we will learn additional things about these galaxies. And then we will have basically, from there on, we will be able to apply with even more confidence, all this physics and what we have learned to the early universe. Because remember, if we want to go beyond redshift 3 or 4, basically above redshift 4, the intergalactic medium, the Lyman continuum becomes opaque. You can never observe the Lyman continuum at high redshifts. So any study you want to do above redshift 6 needs to use indirect indicators. And those we will have validated and we at redshift 0.3 and at redshift 3 over a significant fraction of cosmic time. So that's hopefully what the James Webb will be do soon. It seems to be perfectly running with specifications which are even better than with an instrument which seems to work even with a telescope, which seems to work better than SPECS. Furthermore, the James Webb has more fuel than planned, so it will be able to work for more than 5 years. We hear 10 to 15 years. So there is a great time coming up for the James Webb. And I think, as I summarize here in these conclusions, we have learned already important things which will allow us to go on and study the epoch in the early universe based on the findings we have right now. And I think I will stop here and thank you for your attention and take questions instead of summarizing the conclusions.
Thank you very much, Daniel, for this talk. And now we have the talk open for questions. Please raise your hand. And we have the first one, please, Rosa.
Hello, Daniel. Nice
Hola,
to see
Rosa.
This was very, very interesting talk and beautiful result. Well, I think that the main problem of this kind of research is that many of the quantity that you need to measure need a very good signal to noise, because you are measuring flash which is close to zero, so that means that you are in many cases could be dominated by the noise of the spectra in the Lyman continuum or in the UV absorption line. And I wonder if I suppose that you have already studied how much of the dispersion that you have in some of the correlation is related with the signal to noise that you have in your data, and in other case, it is more related with it is not really correlated with the signal to noise, it is more correlated with the possible geometry that the H2 region could have to favorite or not the escape of from the galaxy. Could you please comment this?
Yes, sure. There are different things in your question. I think the first point was the signal to noise and so on. So indeed, we have the signal to noise we have, and it's variable. And even with HST, it's not perfect, and from the ground, it's not perfect. But some things will be easier to measure with James Webb, and some not. But that's of course a limitation. But I think the point is that, as you've seen, I don't know if I should share again the slide, but I think you've seen the point. We have a list of 10 different indicators which we can use, and of course in some galaxies we will be able to measure several of them. In others we will be only able to measure one, and that depends on the type of galaxy you're looking at, on the brightness and so on. So we will never have all the indicators together at to infinite signal to noise, but it's really the best we can do. And I think and we see, you know, and we have to progress. But for now, of course, you know, there will be not necessarily a unique indicator which is going to be used for all galaxies. Some will be easier to measure, but you know, I think that's indeed we cannot do better. But I don't think that. But you know, the James Webb is going to deliver quality spectra, you know, of similar quality, which we can get for redshift 0.3 galaxies at redshift 3, 4, 5, and so on. But okay, I cannot give a general answer. And then there will be ELT, you know, which will be able to take UV spectra of galaxies with you know, with incredible sensitivity and so on. So now to the second question, the second part was whether the scatter in these different correlations we find, whether it's related to signal noise or geometry. We think it's mostly related to the physics, which may not be so simple, and to geometry in part. That includes, you know, that includes part of the complication. It's not in most of the stuff. Okay, some I did not comment in detail. Some of the measurements of absorption lines have large error bars and so on. But we think that the scatter is intrinsic in several correlations. You know, it's not just due to the measurement uncertainties, and it's related to some physics, which could be, you know, indeed some probes, as you were saying, some probes are probes which are geometry insensitive. Others depend on the geometry. Yes, and we're trying to study, you know, what are the secondary effects. There are many different attempts to understand the scatter going on right now.
Thank you.
Thank you, Rosa. Next question. We have 6 more questions. So Pablo Perez Gonzalez, please.
Hi, Daniel. Very nice talk. Thank you. So your results point out that that the Lyman continuum photons escape through holes. So one could question. We could question ourselves. So what is the origin of those holes? If it's intrinsic or it's they are being formed. So in that regard, maybe there could be a correlation with the age of the stellar population. So have you looked into that? You showed some plots also with the Lyman alpha equivalent width. So maybe in that regard, have you seen anything related to the age of the stellar populations?
Yeah, it's a very interesting question. I had no time really to discuss about the feedback and what we think could be causing these holes. Empirically, and indeed, what we found is that the strong leakers, we find evidence for very young populations. So very young means less than 10 million years, certainly. In some cases, we think that these galaxies are dominated by, you know, 2 to 3 million years population. What that implies, at least naively, is that there have not been many supernovas, or maybe not even any supernova going on. So I think we have some evidence that, you know, supernova cannot be the only thing which produces holes. There must be other mechanisms of feedback, and people are studying that. For example, there are some hydro simulations which show that you can get instabilities in winds driven by star clusters which break up and create channels and so on. But it's really it's a whole field which is going on now, and people are starting to simulate this. But for example, you find in the literature simulations of cosmic reionization from different groups, which include only feedback from supernovae. And one result they obtained, for example, in the initial Sphinx simulations, they said, for example, you know, we need binary stars to reionize the universe. Why is that? Because in their models, feedback comes from supernovae. Supernovae kick in only after basically 10 million years. And at 10 million years, you do not have normal stars anymore to produce ionizing photons. Therefore, you need binaries which produce ionizing photons later. But you know, if you had another feedback mechanism which comes in earlier, this whole picture could fall apart. And in fact, I think it's still open, but I think, you know, there must be other feedback mechanisms. We do not have, to come back more precisely to your questions, we do not have a very clear correlation of F escape with age, for example, something like that. But we think that many of the galaxies are really dominated by pretty young populations.
Thank you. Next question, Enrique Pérez Montero. Go on, Enrique.
Hola, Daniel. Thank you very much for this very nice talk, very well explained and developed indeed. I have a brief comment. First of all, just to remind that we have developed another indirect method to derive the fraction of escaping photons using, you know, helium-1 over helium-2 in combination with optical lines, that we think that it's quite useful as well when the galaxy combination is emitting helium-2 with a nebular origin. And second question is about, I'm worried about what's the similarities between the analogs we detect at a low redshift, such as, for instance, Greenpeace, and the real reionization responsible. For instance, from the chemical analysis, we have analyzed that indeed Greenpeace, for instance, are metal poor, but they have traces of other secondary elements, such as nitrogen, for instance, that may indicate that they are not young objects, they are evolved. So the main responsible for the burst of star formation is the inflow of preceding gas from the cosmic web. Taking into account that the cosmic web in the reionization epoch is denser and the amount of available gas is larger, I wonder to what extent the fraction of escaping photons in the analogs can be taken as a proxy for the same thing at the reionization epoch. What do you think about this?
Yeah, it's a good question. I mean, as I was trying to say, I think what we can say is that every property we have been able to measure at low Z, and for which we have some estimate or measurement at high Z, they basically agree. But for example, it's true, we don't know, for example, the nitrogen abundance of high Z galaxies in the epoch of ionization. Maybe they are going to turn out different. And then it's a question, you know, if something is different, does it mean that the main properties are different and that's, you know, we cannot learn from the physics of low Z galaxy? I would say, you know, if the laws of physics are the same, I don't think you know, we should have fundamental worries, because we are looking at extreme objects which are, we know already, they have a very high pressure and density in the interstellar medium, the green piece, for example. And that is very uncommon at low Z, but at high redshifts, that's what we see. Galaxies are more compact, they have a higher ISM pressure and so on. So it all goes in the right direction. But of course, and then some theories say, yes, but these galaxies, they live in a different dark matter halo at high redshifts. But, you know, maybe that's right. But, you know, does the properties of the interstellar medium and the star formation in the center of the galaxy care about the exact dark matter halo properties? I'm not sure. And all what matters is basically, you know, the amount of gas you have and the energy, and then to create a structure so that it can escape. But, you know, maybe we're going to discover something that's a limitation, and that's what we want to do, for example, also by comparing redshift 3 to redshift 0.3 with James Webb and Hubble. Then we will have a time basis of 8 gigayears to compare. But yes, you know, it's of course I think these are the only ways we can approach it. We can approach it with simulations and compare, and with observations and compare. And I'm doing the second one.
I agree. Thank you.
Thank you, Enrique. Next question from Carolina Kering. Carolina, go on.
Hola, Daniel. Thank you very much for this very interesting talk, and good to see you. Yes, I have two questions. So the first one is there any required minimum value for the escape fraction for a galaxy to be considered confirmed Lyman continuum leaker, or just a non-zero value is enough? And the other question is how frequent nebula helium-2 line is observed among the Lyman continuum leakers? So have you looked into this?
Yeah, the first question is when do we consider Lyman continuum emitter? Lyman continuum emitter, it depends really on the paper and so on. You know, we think if for, let's say, for cosmology or to explain cosmic ionization, you need to have a significant production. So the product of production times escape has to be significantly high, and that means that you typically you have to be above 5 or 10% or so. Now we see also that the galaxies we're observing, they actually produce more ionizing photons than was assumed in standard way. So in fact, you could say then if they produce 2 times more, then already 5% escape is cosmologically relevant, right?
Okay.
So it depends a bit on that. Yes, now regarding helium-2, yes, in fact, I did not include this because I had already a lot of material, I think. We had a paper from a postdoc, Rui Marquez Chavez, who some of you know in Spain, with whom we studied actually the behavior of helium-2 in the Lyman Continuum Survey. And we did this with stacking of STSS spectra and by looking at individual spectra of some objects which we observed with deep X-shooter spectra. And the bottom line is quite simple. I think in any spectrum we have seen of Lyman continuum equals, we did not notice any particularity with helium-2.
Okay.
Helium-2 is, as you know, is present in many low metallistic galaxies, but it's not stronger in leakers and it's not weaker in leakers. There seems to be no significant change with that.
Okay.
That's explained in the letter which was published recently from Rui Marquez Chavez, and I'm co-author. If you want, anyway, you will find it. And I think, physically, there is no reason there should be a correlation, because one is related to the hardness of the sources in the galaxy. And as you know, and as many of you online know, we don't know exactly what causes, what produces the photons, what emits the photons to explain the nebular helium-2 line. But, but to have an escape, you need to have either completely ionized ISM, or you need to have holes, and you need to have some ionizing photon productions. That's all you need. And that's not related to the exact hardness at high energies or whatever. So, I think it makes sense. And we would not expect a correlation.
Okay. And what fraction of the confirmed Lyman continuum emitters has been detected in the X-rays? So is there any study on this?
There's no systematic study on that, but no, not that I know of. The difficulty is that the overlap with X-ray catalogs and so on is probably not so good, and deep observations have not been done. Yes, okay. But I'm sure on this. I agree on this topic, and related to helium-2 or not, it would be interesting to have more multi-wavelengths data.
I'm asking because maybe outflows produced by accreting objects can help a Lyman continuum leakage. I'm just wondering if this is possible.
Yes, it's true. I think there is one paper around like that, which makes tries to make some connection between ULXs, and you could say that if X-ray sources, if they have a significant feedback, then they could drive escape. There could be a connection. Yes.
Okay, thank you.
Empirically, I think we don't see it, but it would be interesting. And also going other wavelengths. Oh no, maybe I should leave time for our next question.
Okay. Yeah, thank you very much.
Thank you.
Thank you, Carolina. Next question by Almudena Prieto. Almudena, please.
Yeah, hello. Hello, thank you very much for the presentation. I just wanted to make a comparison with things that we know are redshift 0. And many things that you were saying reminds me a lot of what we are finding, for example, in young stellar clusters. We can resolve young stellar clusters in nearby systems. And we have done that in a number of cases. We resolved hundreds of them. And it turned out that we can measure the leaking of Lyman photons very accurately, because we can model the spectral distribution quite accurately, and we can infer what is the budget of emission photons. And it turned out that it's enormous systematically, no matter what galaxy is. In fact, one say might depend on the cluster, or the mass of the cluster is not, or the size is not, or the luminosity is not. They have very little dust, as you find it. Of course, they are global compact clusters, they are very compact. And we've conclude is something that has been already proposed since long, that the H2 region is optically thin. Therefore, the leaking of photons is enormous. And we can compare that because we know how much H alpha we measure from the cluster and how much we produce. And it's 80, 90% very high. So if you put all these clusters together in your galaxy, you will see something very compact. And maybe you infer as well enormous leaking, but physically and individual regions where the ionizing photons is happening, the leaking is there, and we see already a low redshift. This is something that was already proposed by Ferguson many, many years ago to explain diffuse emission in galaxies. It also happened in the spiral arms, the clusters, the young stellar regions in arms of spiral. So maybe there is enormous, I mean, the scenario you were saying before, the physics is the same, which is good. I like it when we don't have to change physics. But it happened now when we measure, and we measure accurately, 80, 90% or leaking.
Yes, I know. I agree. I did not show any result from these resolved galaxies, but it's very interesting, of course, to see and to be able to try to see, you know, if you have some ionizing cones. The question is, of course, also how it propagates at larger scales. You know, if the photons which escape the individual H2 region, if they get stuck in the gas in the galaxy, or if they really manage to get completely out.
Yeah, that's the thing. I mean, Ferguson was proposing a number of people now when they study spiral arms that they produce a kind of diffuse gas around. If in a spiral galaxy, you have a much more dense interstellar medium. The galaxies I am looking at is just in the center of the galaxy. So I do not know where these photons go, but definitely are not at the cluster level, are not in the circumnuclear arena and studying, are not there, are escaping, maybe in the galaxy around. And so you put this a higher redshift, you see what you are looking at.
Yes. Yeah, no, it's very interesting. There's a lot of things to learn from Low-z studies and resolve studies. Yes, I'm very interested in that, and I think we always have to learn, you know, from the different scales and connecting Low-z to high-z. But I know several people in Spain also move between Low-z and high-z, and that's important. You have a lot of knowledge and expertise on this detailed star formation. It's very, very, very important.
Thank you.
Thank you.
Thank you, Molina. Last question that I have here by Pepe Vilches.
Great talk, Daniel. Thanks a lot. Most of the question has been already answered by others. So my only bit which is missing, or I expect for you, is, for instance, if you have any summary or idea, summarizing idea relating the leakers or the leaking fraction and the kinematics as seen from the spectra. So are there hints or good observations to linking, for instance, line profiles and kinematics with that? Or thanks.
Yes, thanks. So the question.
Just a summary. I don't want to make it that much long.
Yes. No, as you know, indeed, we have obtained, and Ricardo Amorin, who has been, I don't know if he's still in Granada, if the school is still going on this week.
He's visiting.
Yes, okay. So with Pepe, Ricardo, and others, we have obtained X-shooter spectra of some of the leakers to precisely try to study the kinematics of the gas in these galaxies. And I don't have a clear overview yet, but what we have seen initially is that in several of these leakers, in many of these leakers, they show actually broad extended emission lines in the O3 and H alpha, for example, which shows that there is a fraction of gas, maybe even a significant one, moving to quite high velocities, means up to 1,000 kilometers per second. We had looked also at the kinematics of the low ionization lines, where in fact we saw that they are not moving very fast. So it seems like, you know, the clouds where the clouds which are in the galaxies, they are relatively static. They contain the dust and the metals. And probably, I think, in the holes, you know, you have just gas which is blowing out, and it goes much faster because the way is free there. In the other parts, it's stuck. So, and in the channels, you can, you can just freely escape. I guess but we need to quantify this. But this is more or less what we seem to see. Now, what causes this? And if we can explain, I don't know, the amount of gas we see at high velocities, and if we can accelerate easily to 1,000 kilometers per second, I don't know. That's things which need to be worked out. But yeah, it's an interesting dimension, the kinematics.
Thank you, Daniel. See you.
More work to come.
See you, Drew.
Thank you.
Okay. Thank you, Daniel, for the answers. Thank you for the questions to everybody. I think there is no more questions. We can close the talk now. And thanks again, Daniel. And we will wait you in October here for more discussions.
Yeah, thank you very much. And I very much look forward to see you in October. It will be very nice.
See you soon. In
It'll
October.
be a pleasure.
Thank